This puzzle's called It's the Magic Number by Maff. I got it from the Discord Puzzle Archive on the CTC Community Discord. Let's take a look at the rules. So normal 9x9 rules. Cells separated by an X, sum to 10s, separating by a V, sums to 5. The center cell for all 9 boxes. Let me just highlight these. The center cell for all 9 boxes can't contain a repeated digit, so it's a set of the digits 1 to 9. Okay. The question mark outside the grid is indicating 2 diagonals with each independently summing to the magic number. Each row and column within boxes sum to the magic. Each row and column within boxes, I guess that's all boxes. If a box sits on one of the 2 main diagonals of the puzzle, then the diagonal also sums to the magic number. The magic number must be determined. Okay, I think I do understand this. So, 1 second. Sorry, I'm just getting over a cold. I haven't been coughing. Except for right then when I started reading the rules there. Sorry about that. So these 4 digits, let's make them pink, are going to sum to some number. We don't know what that number is. Then every row and column in 3x3 boxes is going to sum to that same number. So these and this and let's go with blue. Pink, yellow, and blue all sum to the same number, as well as every other row and every other column. Also, the diagonals along the main diagonal, the diagonals within a box along the main diagonals also add up to that same number. So like these 3 are going to add up to, these gray cells are going to add up to that same magic number. Now this might be kind of a difficult puzzle. It is rated kind of half 3, half 4, even a couple, I actually didn't notice that, even a couple 5 out of 5 difficulties. But it's rated very highly in terms of like in enjoyment. We have 6 out of 6 votes for exceptional puzzle, so that's really good, and 7 votes for beautiful logic, 1 for mind blowing. So it's super high ratings. So I'm going to put a link to the puzzle down below if you want to give it a try. This one might be a bit difficult. So let's do that. Let's get started. I don't know if I want to leave the light green there because I have a feeling we're going to need a lot of coloring. But yeah, I have a feeling we're going to need a lot of coloring, but I need to remember this disjoint set thing. So the first thing is figuring out the magic number, which is actually pretty easy. If we look at any box, any full 3x3 box, any full row, any full column, that's going to contain the digits 1 to 9 exactly once each, of course. So if we add up all of these digits, that's going to be 45. It doesn't matter the order, it's still going to contain the same digits, but that full row or the full column or the full 3x3 box is going to contain the digits 1 to 9. That adds up to 45. So if we divide this 45 into 3 different columns, let's say, each column has to sum to the same amount. So if we have 45 and we divide it into 3 equal parts, that's going to be 15. So I believe the magic number is just going to be 15. Let me just look. Each row and column sums to the magic number, right? So each column here is going to sum to the same amount, and it fully fills this 3x3 box. So that means all 3 areas together sum to 45. They're all equal, so that's 45 divided by 3 equals 15, right? Just had to go over that logic again to make sure I got it correct. So we have a lot of 15s in 3. So maybe it's worth it to look at all the 15 in 3 combinations. There's a lot of them. I'll put this up on screen in a moment. I'm just copy pasting a little bit from a list of combinations. Okay. Let's pop that up. So these are the different combinations that of 3 digits that sum to 15. That might be useful sometime later, I'm not sure. Where do I start? Where do I start? So we know these three sum up to 15. Well, okay, maybe this is the place to start. This is the place to start. So this is, I believe, a traditional 3x3 magic square. If you haven't heard of this, it's yeah, it's just there's just a kind of a mathematical thing that sometimes you look at maybe in like elementary school or middle school, where you just put all 3 digits into a 3x3 grid like this, exactly like this, and the diagonals are all the same, the rows are all the same, and the columns are all the same. I mean, they add to the same number, which again is 15. Um, Now the to accomplish that, 5 must be in the middle of that, and then we have pairs of 10 digits, um, or pairs of digits that sum to 10, uh, like in opposite sides of the 5. Now the next thing that you just kind of need to know, or you can figure out of a magic square, is that the corners are always the odd numbers, 2, 4, 6, and 8. And then so then the ones adjacent to 5 are 1, 3, 7, and 9. If we tried to swap it, we would end up with, I mean, with the even numbers in the middle, we would end up with an even and 2 odds along these uh, rows and these, or this column and this row, and all the rows and all the columns, all the outside rows and all the outside columns, which would be odd plus odd plus even is an even number, and we need to hit 15, so that won't work. So this is at least one step of it, is this magic square. And there is, if we start getting a little bit of information about, like, if this has to be a 2, then this has to be a 7-9 pair, this has to be a 4-6 pair, and so on. So if we can get a little bit of information, there's actually only, like, one configuration that works. Now that one configuration can be, flipped around or rotated, of course, but it's not like there's a lot of leeway here if we can figure out where to go. So we know that none of these have 5, I guess. Maybe that's important. We have that center cell disjointedness. So we can't put another 5 in on any of them. So that's gonna be interesting. That definitely is interesting because this is like almost a magic square, a traditional magic square like this, except one diagonal does not sum the same. Oh my gosh. Okay, so and we have to do the same thing on each of these, but with using different numbers in the middle. Okay, well if we put a 1 here, would that even be possible? I don't think so, because we would need this to sum to 14, and this to sum to 14. That's possible, but we also need this diagonal to sum to 14, and that just wouldn't be possible. So we couldn't put 1 in any of these 4 cells because it would end up being the same situation. I think similarly 9, because we would need the adjacent digits to add to pairs of 6, but then we would need the diagonal to be a pair of 6 as well. And it'll work down here, or actually let's do over here just the same. These would have to add to 6, these would have to add to 6, but then the diagonal would have to add to 6 as well. So those don't work. What about 2 and 8? I guess that's a reasonable thing to ask. If this is 2, this has to be a 13 pair. Unfortunately, there's 3 ways to make 13. I don't see that that's immediately broken, but let's just take a look. So there's 3 ways of making 13. So what are the last 2 digits? Would be 1 and 3 along here, if this was a 2. because we need a 13 pair here, and here, and here. Now this, so one of these will be, maybe we can rotate that. We don't care which way this goes, because this could be, the whole box could be kind of flipped along this diagonal. So we'll just look at this example. This is a 2. This needs to be either, yeah, this needs to be something that sums to 14 and this. So this could be 5, 9, or 6, 8. So this is 5, 9, or 6, 6, 8, which leaves 4 and 7 over here, which means this needs to be 6 and 9 over here, and 5, 8 here. Okay, so this sums to 15. This sums to 15. Yeah, this will be a pair of 13, so this will sum to 15. This will sum, will this sum to 15? Let's just, this is 9, this is 4, that makes, this 7, this 6, this has to be 5, this sums to, or this must be 8. That's 12 plus 3. Yeah, that seems to work. And if we, yeah, and in this case, this is symmetrical over this diagonal. If we made this 9, but if we made this 9, it would be exactly the same, just, flipped over. Okay, so 2s do work in the corner, and I assume 8 works in the corner, but in an opposite way. So 8 needs 3 different ways of making 7 along these diagonals. This is not necessarily the 2 box, I'm just testing stuff and seeing how things work. So this is 1, 2, 3, 4, 5, 6. This will be 7 and 9. We can just guess that this is 9 and this is 7. We don't know. Obviously, this actually can't be an 8. That's good to know. This can't be an 8. Okay, I'll have to remember that. Because of this V, we need to put a low digit here. Anyway, now we need this to sum to 6, and this to sum to 6, so we can't use 5 and 6 up there. So 5 and 6 go here. We need a 1 and a 2 across from that. That leaves 3 and 4 along here. And that seems perfectly reasonable. If this is 2, well, forget about this side. Let's just do this so we don't run into more errors. If this is 2, this is 1, 6, 5. Now we need this to be... Oh, wait, does this break? Or did I do this wrong? This needs to sum to 8, so this would have to be 5, 3. So this has to be 2, but then this is 6, and this would have to be a 2. If 8 doesn't work, why does... Let me go over 8s again. If 8 doesn't work, why does 2 work? To me, it seems like both should be broken along on a diagonal, or both should work. Let's just analyze this again. So if it's 8, we need pairs of 7 along the row, the middle column, and the diagonal. So that's 1, 2, 3, 4, 5, 6 to give the 3 different pairs. So this is going to be 7, 9. We can arbitrarily choose one of them to be 7, one of them to be 9. It doesn't matter because the puzzle's going to, or the 3x3 is going to be symmetric over this diagonal. So now we need this to sum to, oh, that's what I did wrong. These have to sum to 6, not sum to 5. That's what I did wrong. Okay. These sum to 6, so this is not 1, 2, 4, or 5. It's 3, 6. That's what it did. Yeah. So this is 1, 4. This is not 1, 4, so we have 2, 5 there. 3, 6 here, 1, 4. So if we, chose 6, 2 to complete this line, this would be 3, 1, 4, 5, 15, 15, 15, 15, 15. Okay. How do I want to somehow try to save this information for later? I don't think I need to. It's not too difficult to generate these squares. Whoops. So we know the 1 and 9s are in here. That's interesting. So we know the 1s and 9s are in one of the middle boxes, whether it's the middle along the left side or the middle along the top. right or bottom, which is going to give us a decent amount of information about the middle box. Now I guess these could be like this, couldn't they? I was thinking that they would have to be opposite. Yeah, they would have to be opposite, because let's say this is 9. This now can't be 9, which means it can't be 1 either, which takes 3, 7 out of here, and then rules 1 and 9 out of this, so this is left as 1. Yeah, so 1 and 9 are opposite each other. We don't know, of course, if it's up here or down here, or sorry, up here or like vertically or horizontally. If it's here, I'm just thinking because the 1 existing in the row or the column will affect this, because this needs, yeah, because it needs to add to 6, but it can't use a 1, which means wherever the 9 shows up, it's going to have 2, 4, kind of pointing towards the middle box. So let's just look right here, and we can, of course, put this in a different cage. We might have to rotate this whole grid or something. But this is a 2, 4. This would be a 1, 5. Then these would be, what would these be? 3, 6, 7, 8? These couldn't be 1, 9, so then these would be 6, 8. Oh, I guess the same thing worked for the 14 pair. I wasn't even thinking about that. But that is true. Oh, maybe we can... Okay, so these can't be 1, of course. I don't know why I typed 1 in there. Let's just look at these now. So this one right here needs to be a set of 3, sums to 15 without a 1, a 5, or a 9. So let's just copy this list so we can delete stuff from it. So 1, no 5, no 9, no 5. Okay, so we don't know what the middle digit is, but one of these is going to be middle. I'll just write that there so I remember, hopefully. So one of these is going to be a 2, 6, 7 triple, and it could have the 2 in the middle, it could have a 6 or a 7 in the middle. I don't know. And the other one will be 3, 4, 8. Now again, this could all be rotated 90 degrees, and this 9 could be here with the 2, 4 pointing downwards. I guess, wait, that's this pair, or this pair of triplets is going to be all of these, isn't it? Because we have 159 accounted for, I should say. 159 accounted for in each of these middle columns. Oh, excuse me. So, like, let's say this is 2, 6, 7, then this will be 3, 4, 8. Now, we don't know what the middle cell is, but then can we figure out... I was just thinking, could this even be a 9? Let's back up a little bit. It might be that I basically need to guess an orientation and just go with it, and then at the end of the puzzle, rotate everything. That might end up being the case, but I'm not sure. I'm not sure. Could this even be a 9? Because this... maybe I'm thinking about this V too early. Maybe I'm thinking about this V too early. Maybe I should just kind of pick one and commit. And just know that at the end of the puzzle, there's, like a, I don't know, like a 75 or 90% chance that I'm gonna have to rotate, because we choose if it's horizontal, we choose if it's horizontal or vertical, then we choose which side to put the 1-9 on, and then we also choose kind of which direction we rotate. So I guess that's like what we have a 1 in 8 chance of guessing correctly. Okay, let's just commit, because I think that's the best. I think that might be the best way of getting through this. Whoops, not the colors. So this is going to be 5-9. This is going to be 1-5. This is 2. Sorry, this is 2-4. This is 6-8. Now, one. No, I guess we do. Can we reduce this anymore? If this was an 8, it would be 1. This was an 8. Yeah, it would be 1-6. Yeah, that it still works. Okay. For some reason, I was thinking we could reduce this a little bit, but we're still kind of in a symmetrical state where we could flip everything around in 2 different ways, along here or along here. Okay, so we know one of these is going to be a, 1 second, I have too many windows open. One of these is going to be a 2-6-7. One of these is going to be a 3-4-8. And we just kind of have to pick which side we're going to put it. Let's just do 2-6-7 up here. I don't know if this is the right way to do it or not. Is there some way of, like, does it, I feel like maybe we have to guess on each one of these, in which case that's just too much guessing. It's not like, it's not like just choosing one orientation and going with it. I don't know. I could be wrong. Okay, how do we make, I was going to say, how do we make 15 with a 2 without a 6 or a 7, but we have 2 ways to do that. Okay, let's, so we have to use one of these for the 2 row. For the 6 row, we can't use a 2, 6, or a 7. Sorry, we can't use a 2 or a 7. So we have this. Of course, it's not that. But now this breaks it. Because if we tried to do 4, 5, 6, then we couldn't do a 2 column. Sorry, a 2 row. So it can't be here, which then rules this out. Which then makes this, what? 3, 5, whoops, 3, 5, 7? Wait, why did I do 1, 6, 8? Undo. Oh, I know why I did 1, 6, 8, because it has a 6 in it. For some reason I'm still thinking about 1s. I don't know if this is the right way to do it or not. We're getting information, but I feel like there's so many deviating paths that maybe it's not just going to be a symmetry thing by the end. For one of these, we're going to need a diagonal. So let's say this was 2. This would have to be 4, 9. So what's another way? What's the last way to make 2 is 2, 5, 8. Which could work. I feel like all of them are going to have a second option that could work. Because like a 6 could use the 4, 5. This 4 and this 5. And a 7 could use, what's the other one with 7? Are there only 2 ways with 7? Can 7 not be in the middle? Okay, let's back up actually. I definitely skipped a step. Okay, so we ruled that 1-9s can't be here. Sorry, can't be in the corner, so they must be in the middles. And I tried 2 and it worked, and I tried 8 and it worked. So I figured, okay, the more middle digits are going to work just fine, but there's actually only 2 ways of making 15 with a 7. So let's just go through this. We need to do 3 ways of making 8 here. We can do the 3-5, we can do the 2-6, but we can't. That's of course. Yeah, so yeah, I should have realized this, of course, because 7 itself takes or um stops one of the 8 pairs from working. The 1-7 can't be used because, of course, we already used the 7. And the same will work for 3. There's only 2 ways of making 3. Yes, okay. So this is actually like this. And then this is going to be 2, 4, 6. That's interesting that it's the even numbers in the corners, odd numbers here. Now, I'm wondering, is this going to create like a flipped and reversed, like a flipped in 2 directions and reversed magic square on the 5s? Or sorry, on the light greens? I kind of think it's going to. Let me just reread the rules. It's not forced, but or I mean, it's not like directly said by the rules. Was what I mean by forced. That the light greens are going to be another magic square, but I kind of feel like it's going to be another magic square because at least like we're already kind of set up in the same way, and like one of these is going to be a 1-9, which is going to make a 3-7, which is going to make a 1-9, which is going to make a 3-7. Yeah, I'm not sure. That it's definitely going to be interesting to look at. So let's. Can we do anything with these diagonal? Could this be a 2? Maybe this is ruling out a 2. So if this is a 2, I said this has to be these have to be 13 pairs, which I don't know, I'll leave that information down. I was thinking about deleting some of the stuff, but I don't think I need to. So these were 13 pairs. Whoops, these are 13 pairs. If I could select the correct cells, that would be wonderful. So this is a 1-3. Um, and that works with the V. This is a 1 or a 3. So let's just guess that this is 1-3. It doesn't matter. Again, it's symmetric along this diagonal. So, like, if we find something that works, it could, switch the places of the 1 and 3, and it'll still work just fine. So we need this to add up to, these need to be 14 pairs. So this is 5, 9, 6, 8, which takes those away from the options here. So this is 4, 7. So this is going to be, we can look at the opposites here because these still need to be 13. So this is 6, 9. So this leaves 5, 8. Great. Okay. Now let's look at one such option. If this is 9, this is 5, this is 6, this is 8, 7, 4. This is way too big because this has to add up to 15. Now, if we flip this, we started with saying 9 is here. And I think even if we flip this, that's going to flip these two. This is going to become a 6, 9. Oops, I cannot type today. This is the 4, 7. Even still, 9 can't be on this diagonal. So this would be a 9. This would be 7. This would be 4. This would be 6. This would be 8, 5. Now this would be a 4. I guess this is a 2 or a 4. Which makes these two digits the same digit. Oh. Oh no, that's not a problem. I was thinking it rules 9 out of here, which would be a problem, but no, in this situation, the 1-9 pair is here with the 1-5-9 going across here. Okay. Okay. So then this is a 1 or a 3, whatever this digit is would be this digit. At least in this configuration. Which does that break anything? Does having a 1 here or a 3 here break anything? All it does is orient this, because we know this is 267, so this is not 37. This is going to be the 159 that I talked about, which is going to put this is 37 up here, which actually this 1 doesn't even affect this. I was thinking it was just going to set the orientation of this, but that's not actually... I guess if we flipped this over, it would set the orientation of it. I was hoping 2 would get ruled out in that corner, because it would... like, too many big digits, and I guess 1 option did get ruled out, but not enough. Okay, so let's try 8, because I don't think 8 works. Because 8's going to put a big digit there, right? These have to add to 7, which are going to be 1 through 6, which puts a 7 and a 9 up here. Yeah, so 8 can't be in the corner. This corner. Does that then mean that this can't be a 2? Perhaps? I'm not ready to go that far, though. I'm not ready to go that far. Okay, let's try 6. These need to add to 9, so they're 1, 8, 2, 7, not 3, 6, 4, 5. So then this is 3, 9, which would force a 3 here and a 9 here. So then this would be a 2. These would have to be adding to 6, so they can't be 7 or 8. So this would be a 7, 8. Then this has to be 1, 2. Then this becomes 4, 5. And that works. Okay. Or at least in terms of the 15s in the box. Let's see if on a larger scale it breaks. So we have a 3 there. Okay, so what I'm thinking here is this perp for perpendicular. So we can actually just back up a little bit. So if we have 1, 9 here, that's going to make this 159, 159. What happens with the 3? Oh, and then the 159s force one of these to be a 267, one of these to be a 348. And if this is a 3, these have to add to 12. Yeah, without using a 3 would be 4, 8 or 5, 7, which means this can't be 5, 7, which means this is 5, 7. Which is going to make, we can't use a 3, 5, or a 7. Let's just copy that again. There's a 5, there's a 5, there's a 7, 7, there's a 3, there's a 5. So perpendicular to this is 1, 6, 8, 2, 4, 9. Okay, that seems... I don't know how helpful that information is, but I don't think it's bad to write down. Let's look at putting a 2 here again, maybe. No, let's look at putting a 6 here again. What do I look at? Because this... let's try a 4, I guess. I haven't tried 4 up here in this corner. So 4 needs 11. an 11 pair without using a 4, which is 2, 9, 3, 8, 5, 6. That leaves 1 and 7 remaining. Whoops, 1 and 7 remaining. I guess 1 must go up here, so 7 must go there. Which then these need to be not 2 or 3, so then these 2 are 2 or 3. Then these 2 are 8, 9, and these 2 are 5, 6. So this is a 4. So this is a 2, 8, or 3, 7. Does this force anything any certain way? I feel like this is sort of forced to be a 6, but I'm not sure about that. And I don't exactly know how to test it. Like, if I put a 2 here, I would have to test for 2 and 8. Or I guess I could test 6 here and 6 here. Whoops, I meant to be pressing redo, not undo. Okay, so if I put a 6 here, 6 needs 3 sets adding to 9. 1, 8, 2, 7, 4, 5. And then 3 and 9 left over. Which means this is a 3, this is a 9, this is a 7. These can't be 7 or 8. So this must be 7 and 8, which means these are 1 and 2. And these are not 1 or 2. Okay. Well, we have 4s looking over, so this is 5, 4, 1, 2. Why do I have a 2 written there? I don't know. Oh, 1, 2. This is a 7, this is an 8, but that's broken. But is it broken besides this? Like, could this be a 6? Is there a reason why this couldn't be a 6? This would be a 9. This would be a 5. This would be a 3. This would be a 2. This would be a 6. This would be an 8. Besides the XV, is there a reason why this doesn't work? This can't be 1, 9. This is 3, 7, 5, which is what we expect. And like, obviously this orientation isn't working, but could this be a 6 if this is a 4? Maybe I should just undo and do it that way instead. I don't know if this is helpful, because this is looking down more than one option in a row. Okay, what if this is an 8? And this is going to be 7, 9. This is going to be 1 or 3. Hmm. How can I progress without looking? I think there's probably a piece of logic that I could figure out. Can I necessarily... I mean, that would only remove one option. That would just remove 2 as an option here. Let's try 2 here again. I don't think 2 works. I think we're going to get too large of digits. This is going to be a 1, 3. And let's just say this is the 3, this is the 1. Which leaves 4, 7. Which makes this 6, 9, makes this 5, 8. This can't be 9, 7, so this must be 4, 6. This is the 8. This is a 5. This is a 7, this is a 9. So this is a 2, this is a 3. This is 1, 9, or 4, 6. What if I flipped this around? Made this a 1, made this a 3. This is 4, 7. This is 5. Whoops. This is 5, 8. This is 6, 9. This can't be 9 because that puts a 7 there. So this is a 6, 4, 7, 9, 5, 8. Which I guess, oh, 8 always goes here and 8 always goes there. Maybe that's... The diagonal is always... 2 diag is 8 to 5, it looks like. So this would be a 4, so then what would this be? Right, because it's symmetrical along this diagonal. So what would this be? Would be, yeah, the opposite. Would just be 2, 8, 3, 7. Which makes this a 1. Whoops, makes this a 1. And if we put an 8 here, let's say, this is 9, this is 7, this is, these are 1, 2, 4, 5, which makes this a 1, this a 5, this can't be this way, this must be a 6, 2, 4, 3. That seems like it works. And what does that leave? 3, 7, 5? What does it leave here? 8 and 6? Yeah, because there's a threading thing going on, or a roping thing going on here too. But we don't know, until we put the 8 in here, we don't know. Well, what? Are there certain ones this can't be adjacent to? Like, could this be, it can't be adjacent to a 4 here. So if this is a 2, this can't be a 4. What about a 6? What was this, 3, 9? Which makes this a 9, which makes this a 3. I think both times this has been a 9. For whatever that's worth. This is another 1, so this has always been 1, 5, 9 across the top here. And I think that's going to happen here as well. Is that always the case when this is... If this is something else, that wouldn't be the case. Is it? 195 is across the top. No, because sometimes we put 3 up here. We could just swap this and put 3 up there. Yeah, I don't... I think this is the weakest point in the puzzle because of this V. Let's try 6 again. Maybe 2 is just one that works nicely. So we have 3, 9 here, which orients like this. Puts a 2 there. This is 1, 5, 2, 4. This is, what's left is 3, not 3, 7, 8. Which makes these like this. 6 diag is... Do I know necessarily which way it's gonna go? Couldn't I put... If I make this a 5... I don't know if necessarily... Yeah, let's just do it like this. But this is set. We haven't... Except for the 6 itself, we haven't made any assumptions. So could this be an 8? Then this would be 9, this would be 7, this would be 1, 5, 2, 4, this would be 3, 6. And then what's left here is a 9. But isn't that broken? What digits haven't I... This doesn't sum to the right digit. That's why I messed up. Okay. Listen, like, this isn't summing to the right values. It's 6 and 1. How did I eliminate one? Oh, this can't be a 6, of course. Okay, so this is a 6. This is correct. This is a 4, 2. This is then a 1, 5. So this is 4, 2, 1, 5, 7, 8. This is correct. This is correct. This is correct. This is correct. And that does leave the 159 along here. And that leaves... let's just leave that a second. This leaves 159. This leaves... what am I? Leaves 6, 7, 2, and then 4, 8, 3. Hmm. There's a lot of variability here. What about this diagonal? This has to be a 3, which takes the 3's out of there. Which means this is a 1 or a 9, so this is a 1 or a 9. Makes these not 1 or 9, makes these 3s. I don't see why this is broken. And this being 1946 seems to work to me. Okay. Let's hit undo about 50 times. What about 4? Did I try 4 here? I'm not sure. Everything's running together now. So this is a 4. Then these have to sum to 11, which leaves 7 and 1 out. Unfortunately, that doesn't give us anything. So what's... One of these is 1, which... Let's... How do I want to do this? Let's say this is 1, so we can at least get the pairs going. Then this is 5, 9, 6, 8. This will be 2, 3. Which leaves 8, 9 here. Okay. This is 8, 9, 2, 3, which leaves 5, 6 along there. Which puts 5 into here, which is 5 always on the diagonal? I think 5 is always on the diagonal. Because 5 will always be here. Because it'll be a 3, 7, 5 or a 1, 9, 5. Same for this, which means none of these can be 5. Theoretically, 5 could be over here. Let's see, 8 needs 7, so 5 has to be on one of the diagonal, or has to be one of the pairs, so it has to be along this diagonal. 6 needs 9, so 5 is needed. 4 needs 11, so 5 is needed. 2 needs 13, so 5 is needed. Yeah, 5 is always on the diagonal. 5 on... 5 plus 10 pair on diags. Okay. And I can mark that in a moment, but I'm gonna have to hit undo probably a bunch in a minute. So this can't be 3, this can't be 8, this can't be 9, this can't be 2. That means this must be a 1, which means this must be 7. Which means we're arranged something like this. Does any of this stuff see anything? Not that I can tell. Not that I can tell. Okay. What are the two options for this? If this is 7, this is 5, this is 1, which makes this a 5. So this is a 5, this is an 8, this is a 4, this is a 2. So this is a 5 or a 3. Whoops, or a 3. Wait a minute, how could this be 5? Haven't we said the 5? Okay. I might have to start writing down the working pairs for this corner, or the working situations for this corner. This can't be a 5. Fives are going to be along here, so this, and because 5 is always going to be along here, so this can't be a 5. If this was 7, let me just do that again. If this is 7, this is 5 to make 15. This is 1 to make 15. This is now 10, which would put a 5 here. But then 5 is ruled out down here, because this is going to need a 5. So this is 8. This is 4, 2, 1, 5, 7. I don't know. Let's just, this is 6, so this is 3, 7, 5, 8, 6, 1, 4, 2, 9. Top, that's the right side. Okay. So this is the if 6 is up here, this is the orientation. Uh, 2, oh no, 2 is 2 different options. Let's look at 4. The leftovers are 7 and 1, because 1 can't go into an 11. That makes this 5, 9, 6, 8. That makes this 2, 3, which goes with those 2, which goes with those 2. Okay. If we make this, and this is a 4, so if we make this a 9, this is a 5, this is a 3, which is already too high. If we make this an 8, this is a 6, this is a 2, which is not quite too high. Okay. 12, 14, 15, yeah. Unfortunately, that works. I was going to say, maybe we, figured out something that doesn't work, but that's not the case. This is 195, 843, 627. So we have 2 different options so far. Unfortunately, there are 2 options for 2s. I guess putting a 5 here means a 5's here, 5 here, 5 here. I don't see why that would be a problem. This is with a 4, it's a 2, 8. Okay, one thing I am noticing. Let's put in 2's again. This is a 1, 3. This is, let's just say this is a 1 for a second. So, 1 is going to go with, 1 was 5, 8 along the diagonal. Right, how many times did I just say that? It's a 5 plus whatever is needed there. So this is 4, 7, 6, 9. Okay. So now if we look at this cell, in this case, or in these cases, it's always a 1 or a 3. It's never a 2 or a 4. So, this is always a 2 or a 4. That doesn't actually really mean much, does it? Let's hit undo a couple times. So this is always a 1 or a 3. This is always a 2 or a 4. There's always a 5 in here, and here, and here, and here. Did I type? There we go. And I messed up there. Okay. And I messed up there. I was going to say, this pattern doesn't look uniform. It doesn't look symmetrical. Okay. We're almost an hour in. I have exactly 1 digit. I do feel like we're learning, but in both 4 and 6, we have 8, 2 here. That's interesting. So in 4 and 6, these two digits are going to be the same. Maybe we just guess that for the moment. So this is 5, 6, 8, 9. This is 4, 7. Again, I didn't need to do this because I've even pencil marked it now. Okay, so we just guess this for the moment. But this still even has options here, doesn't it? Because we don't know which... Oh no, this can't be a 9. This can't be a 9 because this must be a 6. So this must be an 8. This must be a 9. This must be a 5. This must be a 7. This must be a 4. Because we can't have 9 and 7 on this line. So this is 195, 627, 843. But there's also going to be an option here with switching them, but I just want to look at this. So this is a 4, so this is a 1. Does this always add to 10? What does that mean? Okay, well, let's just write down the last option. So this is 3, this is 1, this is 9, 7, 5, 8, 4, 6. So the last option is 3, 7, 5, 4, 2, 9, 8, 6, 1. And these are all the options. Let's shrink that just slightly. These are all the options for the top right corner. So we always have 10 along here, which means, let's just back up. We always have 10 along here, which means to get to 15, this digit is always going to equal this digit. Which means that the digit is going to be down here. Which means how could we ever have a 2 down here? Because this has this, if this is a 2, we're going to have light pink on this. Right? Like, this makes sense in my head, but let me just test this. If this is a 6, we've said that this must be 3, 7, oops, sorry, 5, 8, 6, 1, 4, 2, 9, and then this can't be a 2. This is a 6, this can't be a 2. Because this must, well, there's a 2 right here. Oh, you know what? Maybe that's, yeah. So if we put a 2 here, and also if we put a 4 here, 2 also goes here. So if this is not 2, if this is 2, this is not 2. If this is 4, this is not 2. If this is 6, this can never be 2. Okay. Hmm. Huh, okay. 4 and 3 could work down here. If light pink was 3, we could have a 4 down here that has a 3, 8. Which doesn't rule out any of these, it looks like, in the middle diagonal. It looks like 5 is always this, although I see. So this is always a 5, so this is an 8, 6, or 4. Which means this is always a 5, this is always a 5, this is always a 5. Okay, so this is a 7 or a 9 always. Um, Is there anything else that really shares a large consistency? I don't see this. I don't see it. If this is so, I guess I know all of these cells. These must be evens, and this can't be an 8 because we can't put a 2 there because these have to add to 10 always. In fact, these always add to 10. So could we? So if this was odd, this would have to be the opposite sum to 10. Hmm. There's always an 8 in one of these two cells I'm seeing, which is going to put an 8 always in one of these two cells. Oh no, I thought there was always a 4 in that, no, but there isn't. This is always odds. 1, 3, 7, 9. So these are always evens. 2, 4, 6, 8. I didn't type those as I was saying them. That was weird. Um, I don't know what that means yet. If this is a 2, I guess there's two options. Okay, if this is a 6, that's here. 3, 7, 5. Could this be a 2 ever? No, this can never be a 2. So 2 is always in here looking downwards. Oh yeah, which is what I proved earlier. Yeah, looking at that. Yeah, whoops. Double proving is what I do. So one of these is an 8. What about horizontally? Is there anything we can see to affect over here? Because this is where we have our other piece of information with the X here. What if we, I guess we could try to make this a 2 and see what happens. And this is an 8. I don't think I need that anymore. I don't think I need those anymore. So this is 7. This is 1, 6, 3, 4. This is 9, 7. These must be 1 and 3. No, these must be 4 and 6. Yeah, and this is 1 and 3. But that's not box 2. This is box 3. I don't know if this is needed or not, but let's just start this. So this, oh no, this is broken. Maybe this is where I needed to look. 7, 9, that's so clearly not allowed there. Because we were forcing 7, 9 along the diagonal. That is actually great news. Anytime I'm reducing options is great news. Could this be a 4? Now this would be a 6. What did I say was like 1 and 7 here? This is 2 and 8. This is 9 and 9 and 3. So this will be 12. So this couldn't be a 1. This would have to be a 7. Because otherwise this would put a 9 here and we'd have a really big number. In fact, this is 12, so this would once we put a 3 here, so 4 can't work either. Oh my goodness. Let me just look at that again. If this is 4, these must be 11 pairs. So the leftover of the 11 pairs is 1 and 7. To match this up to 15, this is either 186 or 726, right? The last two remaining digits are 3 and 9. So if I tried to put a 1 here, this is a 9, and this is way too much for 15. If this is a 7, this is a 3, which is 15, and then we would have to put a 0 there. That's also broken. Correct. Whoops, 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 whoops. So this can't be a 4, so this can't be a 6. Okay. We're actually... I thought the V was the limiting corner, but no, it looks like it's going to be the 6. Or sorry, it's going to be the 6. It looks like it's going to be the top left. So if this is a 6, this is a 4. These need to add to 9. The leftovers are going to be 3 and 9. Okay, that makes sense. So this is 1 or 7. To finish these off, we need either a 2 or an 8. 9, 2, 4, 3, 8, 4. Yeah, that makes sense. The last two are 1 and 7. So this is 8. So this can't be a 7. This must be a 1. Because 7 would be 15 already. So this is 9, 2, 8, 3. This is a 7. This is a 1. What would be the last digit? Would be a... No. For a second I thought this would be a 4, but I just can't do math. This is 9. This would be a 6. Okay. That looks like it works, so we will write it down. 429 861 375. Yeah, now we just have one option left to check, which is 8, which I'm not very confident that it will break, but, you know, breaking anything, we've removed 2 options here, which is more than I could have asked for, more than I expected. So let's go here. The leftovers are 7 and 9, because we need to make 7 pairs along here. So this is a 1 or a 3. That would be great. Actually, we might be able to get a couple of these digits, it's looking like. And actually, I already see one thing. It might be worth... Let's just finish this. But I see in this option, this is always a 2. And if we put an 8, there's a 2 here. But if we put a 6, we have a 2 here. That means one of these two is going to be a 2, which means this can never be a 2. So that must be a 4, that must be a 1, which removes 2 options. So that's going to be really big, but let's just finish this configuration, and then finish things off. I think we're coming down home stretch. Like, so much of this stuff required knowing, like, learning about this puzzle, but there's so much that's, like, reliant on other things that I think that once we start getting more digits besides 5, things are going to fall into place rather quickly. Let's see. So this is 7 plus 9 needs a 6. 9 plus... it needs a 4, which leaves 3 and 1. This is... What did I say? Like, one of these... Oh, this is a 4. This is a 1. So this can't be a 9. This must be a 7, 3. Sorry, my phone just buzzed. Okay, I do need to read that in a second. One of my friends... That doesn't matter. Too much information. But I do need to read that rather quickly. So this is a 6. This would be a 4. 9... 1, 3. That would be 7, 8. This would be 7. This seems to work with a 9 and then an 8. That seems to work. So let's just type this in. 267 483 915. Okay. Now we can hit undo a bunch. Okay. And look for similarities, which is what I did kind of while I was doing it. 4 always looks down, it looks like. 2 always looks to the right. 1 is always in one of these 2 cells. I guess everything is limited to 2 cells, huh? I don't know if that's helpful. There's only 2 options. It only really matters when it's in the same row. I guess 8 is always looking to the right. 6 is always looking downwards. I guess I can just... This is a 4, or I could just type in all the options, huh? Couldn't I? That would probably be maybe easier. This is a 2 or a 6. But we always have 2, so this is always a 4, this is a 1, so we can no longer have these. So we just removed 6 as an option from over here. Okay, I forgot about all the information I typed in. I was wondering, I thought I had forgotten to back up stuff, but I did not. So these can't be 1s. This must be a 9, of course, because this needs to add to 15. So this is a 1. We don't need that coloring anymore. We do know there's a 1 in here, which means this is not a 4. This is now a 6-8. Okay, so it's not a magic square like I thought it was going to be. This can't be a 6 or 8 then, because we have a pair along this disjoint set. This can't be a 6. Could this be a 1? I think what I'm noticing is that the opposite of the 5s is the evens. Which makes me think this can't be a 1, but yeah, I guess this is going to be a 168. 168. Triple. This can't be a 1, so this can't be a 9. This can't be 4. This must be a 2. So this must be 2, 6, 7. 4, 8, 3. I should have looked at this right away. This is 9, 1, 5. So this can't be an 8. This must be an 8, which puts a 2 here. This must be a 3. This must be an 8. This can't be a 3. This can't be a 7. Because this is going to be a 7 over here. What are these last two options? This has to add to 15. This is 11. That's a 4. That's a 6. This is a 519. This is a 267. Okay, these can't be 1 or 9. So these can't be 3 or 7. These can't be 1 or 9, which I guess doesn't help as much, but that's okay. We don't have information on the... Oh, this can't be an 8, of course. This is a 6. This is a 4. Because it's a disjoint set, of course. So this is a 6. This is a 4. These can't be 6s. This is just 3, 5, 7. This is 3, 5, 7. This is 1, 5, 9. Whoops, 1, 5, 9. This can't have a 7. I guess, do both of these work? This can't be a 9. What am I talking about? This just can't be a 9. So this is 9. These can't be 4s, so these can't be 6s. This is a magic box. A magic square kind of on its own. And let's get rid of all the colors and then put this back in so we remember that. 3, 3. So this is an 8. These can't be 1s. These can't be 6s. Okay, so what's left here is 2, 4. This can't be a 4. These can't be 9s. Okay. So this must be 168. If this has a 1 and a 6 in it, the other one must be an 8, which leaves 2, 4, 9. We have this. We need to remember this because we can actually probably just use this right now. This roping here. So this is going to be 2, 4, 9. By roping, what I mean is if you look at these, let's make them yellow. Whoops. Let's make them yellow. Where do the yellow digits go in box 9? Well, they can't go right here. Whoops, they can't go in right here because we already have all 3 in the column. Can't go right here because, again, we have all 3 in the column, so they must go here. What's going to end up happening is that we have this same triple all over the grid vertically. And you can see the same thing happening horizontally with 267, 267, 267. 159, 159, 159, 159. This is going to be 159 as well. Because we need to match it up with the 1. This can't be a 5 any longer, so this is a 5, which is going to put 1, 9 along here, and this is actually going to be the 1 because of that 9. What's left in this column is 2 and 9, which is going to make this a 6, and this a 2, 4. This is a 3, 7. This is a... Yeah, I think we've basically got this solved, and I just need to not make it too many big mistakes for the remainder. This is 1, 8. This can't be a 1 because there's literally a 1, 5 pair right there. This can't be a 4 because there's literally a 4 in the box already. So this is a 9, 2, 2, 9. Okay. Okay. This needs to add to 13 without a... This must be 6, 7. Right. I could have noticed that because I guess I didn't once there's so yeah, one thing I've noticed, and I don't know if this is proven or not, but one thing I've noticed is once you start getting a lot of the same triples around, almost always, like at least every time I can remember, that same triple goes everywhere. Um, Now I don't know like what's the tipping point because sometimes you can have like literally just one set of like three columns roping, um, and that's fine, and then have the other ones just kind of all jumbled up. So I don't know what the tipping point is from the point where it's like, okay, we have a small roping section over here to okay, the whole puzzle's roping. I wonder if someone has probably looked at that and like proven like, oh, once you've done it, let's say 5 times, then the whole puzzle's situated like that. Now I don't know if that's what the answer is, but someone has probably looked at that. There's a lot of smart people doing Sudoku. There's an 8 right here, so neither of these can be 8s. Neither of these can be 2s. 2's up here, because it has to be opposite of 8s. So this is a 4, this is a 2, this is a 6. I guess I could have just done this. It was a 2-4 pair, making that a 6. This is an 8 then. This is a 9. 1, 7, 3. Let's see. This is a 4, 2. Whoops. I was saying 6. You could hear the S noise. I didn't make a mistake in logic. I made a mistake in typing. 7, 6, 5, 1, 3, 8. Woo. Okay. Let's just double check because it doesn't check everything itself. 2, 6, 7 adds to 15. So that's roped all around. That's fine. That's 8 plus 7 is also good, and it is everywhere. Okay. 915 is also everywhere, and that adds to 15. Okay, good. Let's do verticals. 249 is everywhere. Good. That's also 15, and it's everywhere. 735 is 10 plus 5. Yep, that's good. That seems to be everywhere as well. Okay, so let's look at the diagonals. It's 10 plus 5, 10 plus 5, 10 plus 5, uh, 10 plus 5, 10 plus 5, 10 plus 5, 10 plus 5. I think that's all of those, so let's look at these two. 10 plus 5, 6, 7 plus 8 is 15. Wow, sorry if you can hear my chair. I just leaned back in a celebratory stretch, and it is a very loud chair. Yeah, that was amazing. Um, that was, yeah, that was definitely a 4 out of 5, in my opinion, maybe a little bit higher. Thank you for that, Maff. That was a great puzzle. That was tough. An hour in, I think I had like literally this 5. I might have pencil marked the 5s by that point. I should have started doing the options a lot earlier. But I didn't think I would need to do that. But yeah, it became once I started doing the options, it became clear. It became clear how things were working. Um, so I just needed to do that sooner, and that could have probably shaved off 15 minutes and gotten me in under an hour. But I'm very happy with that solve. That I just got through it basically. Thank you, Math, again, and thank you all for watching.